Hi, my name is Jim, and today's topic is amplitude modulation, and this occurs when a high-frequency carrier, and carrier means it's going to carry information, is modulated by a lower frequency signal, sometimes called the intelligence signal, which can be speech or music or data perhaps or whatever. The first amplitude modulation transmitters were spark gap. And if you want to get a good idea what that is, watch the movie Titanic. And they were using Morse code, sometimes referred to as international code, to send out a distress signal. And that distress signal basically turned the carrier on and off in a defined sequence in accord to the code. So they were sending out SOSs, and that would be 3 dots, followed by 3 dashes, followed by 3 dots. And what that means is, from the standpoint of timing, that a dash is 3 dot periods. And other than that, there is no other timing associated with it. So the receiver can tell a dot from a dash. There's also time between the letters, so the receiver can differentiate when one letter begins and another letter ends. Uses a type of coding that assigns the most common symbols, in this case that would be the letter E, to the smallest code word, which would be a dot. So this was around in the beginning of the 1900s, and this here represents on and off carrier pulses for an S. And this is a very, very dirty system. I once witnessed a true spark gap transmitter in a radio museum in Rochester after hours. The instructor knew somebody. They're illegal to use, and he didn't have an antenna connected to it, but he lit it up. And there was a motor with teeth on it, where the teeth in a stationary piece of metal separated, arc. Lots of voltage, lots of current, and the sound of it was deafening. So that's where it started, and the reason it's illegal is if we look at the spectrum in the frequency domain, we see it's quite broad, so it's very difficult to channelize it. Interferes with everything, and for that matter, when standard radio became possible in the early 1920s, spark gap transmitters were outlawed, except maybe for marine use. So that's one type of modulation scheme, and carrier amplitude is either 100% or 0. And that's not the case with the AM we're going to be discussing from here forth, except for data transmissions at the very end. So we have a carrier, and the carrier carries the information, nothing more. It does not contain information, and other than it's needed for decoding the signal with the receiver, it's basically useless. The reason that it began in this manner is because the electronics back in the day weren't sophisticated enough to use any other type of modulation. So the frequency carrier with respect to time is V peak 2 pi F carrier times T volts. And for an example, we could let the carrier frequency be 1 megahertz, which would fall in kind of the center of our commercial AM band. Now the modulating frequency in this example is going to be 1 kilohertz. Typically it's speech or music or whatever, and I've designated that F of mod of T equals Vp sine of 2 pi F mod of T volts. So these should be very familiar equations, and the modulation does not have to be a sine wave. Like I said before, it can be music or speech, but in the analysis of this we're going to be using sines everywhere. So what we see here is that we have a high frequency carrier and a lower frequency modulating signal, and then what we have to do is combine them, and that's sometimes called mixing, and in this case it has to be non-linear. An example of a linear mixer would be a mic mixer in a public address system. Don't want any distortion. in this mixing, the whole purpose is to generate cross products. And if it wasn't for nonlinearity, we wouldn't have modulation. So what we see here is that the modulating signal is superimposed and controls the amplitude of the carrier signal. Now what I've shown here is a 100% modulated signal. If it goes any higher than that, it'll cut off the carrier in this area, and that produces what's called splatter, which means that our signal at 1 megahertz can be all over the spectrum above it, so the FCC really doesn't like that to happen. So the range of amplitude can be between 0 and 100%, and not to exceed 100%. So this is the period of the modulating signal here, and these black lines I've drawn are not really present. It's just to outline the shape of the carrier, so you would not see the black lines on a scope, but what you would see would be the red here indicating the variations in the amplitude. Now, if we look at this in the frequency domain, what we see is a carrier without modulation is simply going to be a spectral spike, and all spectral spikes are sine waves at 1 megahertz. And then if we modulate it like this, is we're going to see 3 spectral spikes. One is called the upper side frequency, or the upper side band, and it's simply equal to the carrier frequency plus the modulating frequency, and a lower side band, the carrier frequency minus the modulating frequency. So the range of frequencies for this example would be 999 kilohertz to 1.001 megahertz. Now, this type of AM is called double sideband full carrier. 2 sidebands full carrier. And the acronym for that is DSBFC. So there are obviously other kinds of AM, which we'll be talking about briefly. Now, for example, long-distance telephone networks, not anymore, they're digital, but back in the 60s and 70s and before that, used D channel banks, which were basically analog. And what they did is they took telephone conversations, and speech fits well into a 4 kilohertz band, and they kind of stacked them all up. And what the telephone companies wanted to do was to get the most conversation they could over a minimum amount of bandwidth, and then this would be transmitted, say, by coaxial cable or by microwave. Didn't have fiber optics back then. So to get the bandwidth down, what they did is they only sent 1 sideband. Okay, and 1 sideband has redundant information with the other sideband, so they didn't lose anything. And the carrier takes up quite a bit, so they suppress the carrier. So this is referred to as single sideband suppressed carrier, and the acronym for that would be SSBSC. And it's harder to decode this because you have to, at the receive site, regenerate the carrier and insert it to pull down the voice. Now we have another type of AM which most people don't realize exists, and that associates with FM. Frequency modulation, and that'll be coming up as a topic soon, but there's a left plus right component, which is the monophonic component, and a left minus right component, and if you add those two together you get 2L, so that would be the left channel. And if you invert one and add them together, you'll get 2R, which is the right channel. Now, one of the things they had to do when stereo FM came about is maintain compatibility with monophonic FM, because a lot of people spent considerable money on an FM radio. They were more expensive than AM. So the scheme that they came up with is to take the left minus right channel and code that in double sideband suppressed carrier, and then use that to frequency modulate the carrier wave. So an FM signal has the L plus R, which is regular monophonic, A component of it is double sideband suppressed carrier, which is the left minus right information. And then sometimes you have ancillary broadcast carriers on top of that for, say, Society of the Blind or things like that. So there are several types of AM around. Now, if we take a look at commercial AM, the FCC allocates a 10 kilohertz bandwidth. And what that means is that the maximum modulating frequency can be 5 kilohertz. Now, why not wider than that, so we could have high fidelity, say like out to 15 kilohertz? And back in the 20s, nobody thought of that. You know, it was amazing that you could get speech to be received on a radio. So if we look at the sidebands with music or speech, is what we see is they occupy positions from the carrier, and this is the lower side frequency, out to the carrier minus 5 kilohertz, and then the upper sideband, upper side frequency, would be carrier plus 5 kilohertz. And all this means is there can be a complex waveform in here that has many frequency components, like, for example, speech. So that's what the spectrum would look like. And if we actually looked at this on a spectrum analyzer, is we would just see stuff jumping up on either side of the carrier. Now, important, the carrier never changes amplitude with modulation. It's always there. Case in point, when nobody's speaking over a clear channel AM station like WTAM, 50,000 watts sits there and burns. Carrier's present. Does not carry information, but standard AM needs that for the receiver. So they got a power meter spinning around out there that really isn't carrying information. This is not true in FM. In FM, sometimes the carrier is 0, but that's a whole different modulation method. So if we take a look at this here, we need nonlinear mixing, and what we're talking about is cross products, and this reflects back into M and N as we discussed before. So to get a nonlinear mixing here, we're just going to multiply FC, the carrier frequency, by the modulating frequency, and we get standard cross products. The result of this is a component at the carrier frequency and at the modulating frequency, the carrier minus the modulating frequency, the carrier plus the modulating frequency, 2 times the carrier plus the modulating frequency, and so forth, just like was discussed for cross products. Now the ones of interest that are going to be filtered and sent are the carrier, FC minus FM, and FC plus FM, and that'll generate our carrier plus our upper and lower sidebands. So how are we going to measure all of this? And the coefficient of modulation is referred to as M, and that's lowercase m. And we have an uppercase M too, which is simply lowercase m expressed as a percent. So we multiply that by 100%. Now, in the case of 100% modulation, which produce the loudest sound coming out of a radio, is we have the modulating voltage, and what they do here is they use E instead of V because that's the source, but don't let it confuse you. It's the same thing as voltage, just a different symbol. Years ago, E used to be a voltage rise source, and V used to be a voltage drop. So, anyway, under 100% modulation is what we see is our carrier sitting here with 10 volts, and a modulation is applied at this point. And when the modulation is applied, it goes up to 20 volts and down to 0 volts. So in that, we can see that the modulating voltage is equal to the carrier voltage. And when I say equal, is that the carrier voltage is going to be 10 volts, and the modulating voltage here is going to be from here up to here 10 volts. Or if we look at the peak to peak, the modulating voltage would be 20 volts. The carrier voltage would be 20 volts, and the modulating voltage would also be 20 volts. So we want to keep the modulation percent less than 100, because greater than 100 produces the splatter, which is very bad. So if that's 100% modulation, what does 50% modulation look like? And in this case, our M is going to be equal to 0.5, and our corresponding voltage is going to be 5 volts peak to peak. So now with the same carrier voltage, we're only going to go up to 15 volts on the top of the envelope and down to 5 volts on the bottom of the envelope. And as you can see, these are symmetric, about 0 volts. So if we have 0% modulation, we just have the carrier, no sound comes out of the radio, and as we increase the modulation percentage, it gets louder and louder. Now some people may ask, why do commercials seem louder than program material? And the answer is that, seeing that the range is 0 to 100%, what they do with speech is they compress it. So the average level of the speech is higher. It doesn't dip down. They don't exceed 100%, but it typically doesn't go down to 0 either. And the purpose of that is because it allows the signal to reach further, meaning more revenue with regard to advertising dollars and so on and so forth. So if we interpret the envelope, if we just saw the envelope on a scope screen, what we could do to figure out what the modulating voltage is and what the carrier voltage is to use these simple equations here. 1/2 of the envelope, that'd be that guy, maximum minus the envelope minimum, and that would give us in this case 5 volts for the 50% range, and the carrier voltage would be basically the same formula, except we'd be adding. And if we do that, we see that the carrier voltage comes out to be 10 volts. Now, an important concept here is that the modulating voltage equals the voltage of the upper sideband plus the voltage of the lower sideband. So what we can determine from that is the voltage of the upper is equal to the voltage of the lower, which is equal to the modulating voltage divided by 2. So the upper and lower sidebands have the same voltage level and they carry the same information. And as you can see, that's kind of a waste of bandwidth. Now this is the equation of an AM signal, so it looks pretty bad, but it isn't really. So let's take this apart. And first component in here is going to be the carrier. So EC, and this will be peak, sine of 2 pi times the frequency of the carrier, and before in the other example that was 1 megahertz, times T minus this quantity here, and this is going to be the upper sideband because we see we have the carrier frequency plus the modulating frequency. The amplitude of this is going to be M times the voltage of the carrier divided by 2. So if M is 0, this whole term becomes 0, and if M is 1, what we have basically is 1/2 of the carrier voltage, and that would represent 100% modulation. And that we add that to the lower side frequency, FC minus FM, and then the same coefficient as I described a minute ago was the same thing. And this 3 terms make up an AM signal. Now, it's not likely that we're going to be wanting to find the instantaneous voltage, and that would be the red line, anywhere. But what this tells us is the amplitudes and the frequencies. So that is what this equation would be useful for if we were to need it. Now, V of T AM can be summarized as the carrier voltage plus the upper sideband voltage plus the lower sideband voltage. And if we just kind of dissect this a little bit, here we have an unmodulated carrier, and during this time period the frequency domain response F would be a single spectral spike representing that carrier sinusoid. And if we modulate it, referring to this area here, M does not equal 0, so we're modulating it, and now we have 3 sinusoids. Spectral spikes are always sine waves. One is the carrier, upper sideband, and lower sideband. And the upper and lower components of this relative to 0 line are symmetrical. So let's take a look at power very quickly. And what we have is an AM source here, I almost drew this with a sine wave and then thought better of it. And this is our internal, and antennas can look like a resistor. Now, the frequency, carrier frequency in this case, because relative to the sideband frequencies, the carrier frequency is the highest frequency. What I mean is that these are close in frequency to the carrier relative to the carrier frequency from 0 hertz. So if an antenna is tuned correctly and matched correctly, it looks like a resistor. Now, electrons shuffle back and forth in the antenna and create electromagnetic and electrostatic waves, which are perpendicular to each other, and those that radiate from the antenna are not returned as a collapsing magnetic field, and that is where the power goes. So, looking at that now, if we wanted to find the power in a carrier, all we would do would be take the peak carrier voltage and multiply it by our RMS operator, 0.707 squared, divided by RL, the load resistance, and then that squaring point 0.707 gives us 0.5, and then your textbook takes this 0.5 and moves it into the denominator. But it's the same basic thing here. So what's not shown in this is the matching equipment and the filtering stuff that has to sit between the transmitter, and this is internal to the transmitter, and the antenna. So if we wanted to find the power in the sideband, it would be P upper sideband equals P lower sideband times the square of the modulation coefficient times the PC divided by 4, and part of that 4 has to do with converting peak power into average power in watts. So what we can see here is we kind of have a nonlinear component with regard to the modulation coefficient. So if I were to say plot that very quickly here, let me do that, and this would be the power of the carrier in watts, and this were to be M, this being 100% and this being 0%, is what we would see is this would rise like this. Now, it's desirable to run a higher percentage of modulation because the power increases significantly as M increases, and that's the ability to reach further for a larger audience. For example, Cleveland transmitters try to pick up the Akron and Canton areas. Why waste power in Lake Erie? So they may have more than one tower to directionally send that into another metropolitan area. And all of this, of course, has to do with the approval of the FCC. Now, if we just take a look at plain old phasers here. Oh, let me go back to this first. So power total, if we break these down, is going to end up being the power of the carrier times 1 plus M squared over 2. Now what we can see here, if there is no modulation, if M is equal to 0, all we have is the carrier power. And as M increases to 1, coming up shortly, that would be a 1.5 multiplier times the carrier power for sine wave modulation. So if we go back here just a little bit here, we want to do a phasor analysis of this because that's pretty cool. Is that in the standard AC circuits, and this would be like the carrier, we have a phasor that rotates counterclockwise, and that if we angle this and move it through space, we'll build a sine wave. That's just the standard stuff for a sine wave. And we're going to move this in positive time. Now, that may seem a little bit ridiculous. If we look at a carrier and have the phasor go counterclockwise, it's kind of meaningless. However, coming up, if we reference the sidebands to the carrier, it's perfectly okay to have a phasor turning in the clockwise direction. So basically what we did is we shifted from 0 hertz up to 1 megahertz, and then we'll analyze the phasors and see how they make this waveform. So before we do that, let's just take a practical example here. We have a carrier power of 5 kilowatts, and there are a number of stations around that run 5 kW. what is the power total if the modulation coefficient expressed as a percentage is 100%, and for the heck of it there I threw in a load resistance and antenna impedance of 50 ohms, and we're just going to consider that to be resistive. So what we have here is 5 kW times 1 plus our modulation coefficient squared divided by 2, and that gives us under 100% modulation 7.5 kW. So the minimum with a sine wave would be 5 kW for just the carrier, and the maximum for 100% modulation would be 7.5 kW. For 100% modulation, the modulating voltage is equal to the carrier voltage, and the upper and lower sideband voltages are the same, and they're simply equal to EM divided by 2. So if we have a carrier, and this is how we got the voltage for the carrier, is P equals V squared over R, or in this case E squared over R, and then solving for E we end up with the square root of P times RL, and since our power here is average power, that's going to give us 500 volts RMS. So EM is also equal to 500 volts RMS, and the upper sideband voltage and the lower sideband voltage are equally divided, so each are 250 volts RMS. So let's check the power using a different technique, and that's going to be the RSS, which stands for root sum of squares. This is finding V effective. Now this is not VRMS because there are going to be three components in this: the carrier, the upper and the lower sideband voltage, and what we want to find out is that power level, which in the above example would be 7.5 K. What is the effective power expressed as a DC voltage? So here's the square root, and then all we do is square the components, and that comes out to an effective voltage of 612.37 volts. Then to find the power is simply V squared over R, and what we see is we get 7.5 kilowatts again. So RSS is very convenient, and you can use this with DC and AC. So if you have a DC voltage with an AC component riding on top of it and you want to find out the power, this is the way to do it. So let's take a look at the phasers here, and I got to bring into play some very high technology camera work. That's pretty good, I guess. And to start out with here is we're going to let our carrier, omega C, remember that's just a 2 pi ft, is going to be our reference, and then sitting on top of that is going to be the upper and lower side frequencies. So as you can probably imagine, the upper side frequency is going to rotate counterclockwise in relative, keyword relative to this. The lower side frequency is going to rotate clockwise. Now the envelope is the sum of these three phasers, and what we see is we're at the carrier frequency here, carrier level here, is that the upper and lower side frequencies cancel each other out, so this would be the value of the carrier only. And then as this increases, this phaser rotates in this direction, this in this direction, and if we add them together we can see that we're a little bit higher on the envelope. Finally, all are added together, all three phasers, where we reach the top of the envelope. Now we're coming down. This guy is the upper sideband phaser, lower sideband phaser. They're equal again and cancel each other out. And then we do the same thing over here, where the sideband phasers subtract from the carrier, and that gives us our modulation, and then the same thing happens at the negative part of 0. So this whole waveform can be constructed with rotating phasers, and I think this is a pretty cool way of kind of describing it. Your author also does this, which is pretty nice. This is a carrier here, and this is 25 hertz, and it's being modulated by a 5 hertz modulating signal. So this is very low, so we can see this easily. And what we have is the upper side frequency is going to be 1/2 of the carrier frequency. The upper side frequency is 1/2 volt, which is 1/2 of the carrier voltage, which is referenced here for ease at 1 volt. And also the lower side frequency is also referenced at 0.5 volts. So here we have the 3 sinusoids which make up our sine wave, our AM signal. And what we note is the carrier phase is relative to 0, and our upper side frequency is a negative cosine wave. And if you recall the equation of an AM signal, there was a negative cosine wave, and then the lower side frequency is a positive cosine wave. So if we add these 3 sinusoids together like we did with the vector, is what we end up with is the amplitude modulated signal, and we see the dots that the author put in there to show that the envelope is not really present. So this is a time domain analysis of what we saw in what I'll call the phasor domain before. Now let's do one more thing with this, and that is taking a look at digital modulation, not spark gap, by the way. So we have a type of digital modulation called OOK for on-off keying, and it's not a very good modulation scheme. There are much more efficient schemes. This is an example here of a remote temperature sensor, and this is the actual transmitter itself here, little guy. And this is an AM modulator which uses OOK. It's very cheap. It's like $4, and it's unfortunately very, very subject to noise interference. And although this worked well here in my basement, sending the temperature from the basement upstairs to the bedroom in a noisy environment with a lot of fluorescent lights and so forth, a lot of trouble. So anyway, with OOK, since we're here, we might as well talk about it, is what we see is the carrier is either full on or full off. So if we assume a 10 bit pattern, 1010, and just consider this to be part of a data packet, say from you're receiving over the radio for some reason, this is the most demanding of a bandwidth, is a 10 pattern. And what you can see in your mind's eye in here is a sine wave forming the base of the square wave. So if we take a carrier modulated, and this diagram I drew is pretty busy, what we end up with is the first harmonic of this guy expressed in the upper sideband, 3rd harmonic, 5th harmonic, 7th harmonic. So what we're seeing here is the upper harmonics being represented in the upper sideband and also in the lower sideband. Now, if I superimpose a sine of x over x on this, is what we see is the null points. And remember that a square wave only has odd harmonics. So 1st, 3rd, 5th, 7th. The null points would be the evens 2, 4, and 6, where the harmonics at that would be 0. So if we went to send this over a typical channel, what we would have is an awful lot of sidebands, and they would all be necessary to recreate a square wave. So what ends up happening is upper sidebands are truncated, so we can fit this into a reasonable sized channel. Now if we only broadcast, the first sideband pair is what we would see coming out of the receiver would be a sine wave at the same frequency. Now that's pretty easy to decode. However, this does not take into effect intersymbol interference. So that's kind of the story here with regard to amplitude modulation, and it's the oldest modulation form. And now what we need to do next is figure out how we're going to detect it. Having a transmitter without a receiver, well, just doesn't make sense. So that'll do it for today, and thank you for watching.